Thank you for the introduction. This is work that I did, that I started during my PhD in Trondheim in Norway, together with my supervisor, Professor Jakob Linder, and then also continued as a postdoc in Akasha's group in Madrid. So I'm going to tell you a little bit about that. And unfortunately, my introduction overlaps a little bit with Wolfgang's introduction, but I guess I can remind you of some of the most important things. So, as you already know, in superconductors, two electrons of opposite spin can go together and create a Cooper pair. And in conventional superconductors, this is a spin singlet Cooper pair, but you can also have the triplet types with a net spin of 1 and spin projection either +1, -1, or 0 along the projection axis. And maybe the simplest example of how to create this in a heterostructure is if we consider a superconductor ferromagnet structure where, how does this work? Yeah, the bands of the ferromagnets are spin split so that there's a different momentum for up electrons and down electrons. And because of this, the up-down and the down-up Cooper pairs pick up a phase which has opposite sign for the up-down and down-up. And if we simply rewrite this expression, we get these oscillating terms where we have this oscillating term where R is the position inside the ferromagnet, and we have the spin singlet pairs and the spin triplet, opposite spin triplet pairs. Now, these opposite spin triplets still have opposite spin with respect to the magnetization of the ferromagnet, so the solution is to add a thin ferromagnetic interlayer where this first ferromagnet has a perpendicular magnetization to the second one, and then the opposite spin triplet created here are looking like equal spin triplets to the second ferromagnet and can then penetrate far inside the second ferromagnet. Now, this you have already seen before. It was already shown that you can create this long-range triplet currents many years ago, where they considered, for instance, in this experiment, a JOHNSEN junction with a magnetic interlayer, where in this magnetic interlayer they had the cobalt layer with an in-plane magnetization and the palladium-nickel layers with perpendicular magnetic anisotropy. And when they considered then the critical current here as a function of the thickness of the cobalt layer, they see that for here these black dots, you have a very rapid decay of the critical current as you increase the thickness of the cobalt layer. This is in the absence of the palladium-nickel layers and in the absence of any misalignment. While if you have the misalignment, this critical current survives to very thick cobalt layers. Now, another important concept when it comes to these superconducting structures is if we put the superconductor between two ferromagnets, and then we can consider either parallel alignment or anti-parallel alignment. And in the case of parallel alignment, we see here that the spin splitting induced inside the superconductor is much stronger than if we have an anti-parallel alignment and the spin splitting field cancels out. Now, another mechanism that is weaker than the first one is whether we consider a parallel or perpendicular orientation. Now, in the parallel orientation, we have this opposite spin triplet Cooper pairs created at the interfaces of both of the ferromagnets, while if we have them perpendicular, the opposite spin triplets created close to the left ferromagnet will look like equal spin triplets to the second ferromagnet and vice versa, and they will therefore be able to leak out of the superconducting region much more efficiently. Now, in these structures, experimentally, it has been shown that this first mechanism dominates, and they found that you have this critical temperature difference between the parallel and anti-parallel. Now, I'm not going to talk about ferromagnets, but antiferromagnets. And while in these ferromagnets we have all the spins along the same directions, you can have two types of antiferromagnets. One has the spins in each layer with spins in the same direction, like this. They have a net 0 spin, but they have a finite spin at the interface. But then you have the compensated antiferromagnets that we are interested in, and they have 0 magnetization in the bulk and also 0 magnetization at the interface. So this seems a bit counterintuitive because we now have a structure where the magnetization of the whole thing is 0. At the interface there's no magnetization. But what I want to convince you is that since we have these local spins, it will still be able to affect the properties of the superconductor. Now, the first work that we did on this topic was looking at an antiferromagnet superconductor ferromagnet hybrid, where we looked at the triplets created from the ferromagnet, how they were affected when they reached the interface with the antiferromagnet. And we showed that whether you have these spins in the ferromagnet parallel to the Neal vector or perpendicular to the Neal vector makes a difference. So just to very briefly outline our methods, we typically consider a tight binding Hamiltonian where we have a nearest neighbor hopping term here. We have a chemical potential which determines the filling of the lattice. We have a spin-splitting field that for the antiferromagnet oscillates from side to side. And a ferromagnetic term which then has this spin-splitting field that is the same on all lattice sides. And we describe the superconductivity as an on-site conventional superconductivity with this gap delta. Now, we write this Hamiltonian in a matrix form, and this allows us to diagonalize it numerically by solving the Bogoliubov-Dejean equations. And through this method, we obtain all the eigenenergies and eigenvectors of the system, and we can calculate observables. And this is really all you need to know, but I will tell you about a few more details for the ones who are interested. Because when we do this, we have to write, we write the Hamiltonian in terms of this, this basis. And here we see that we have doubled our operators from 2 to 4. And what this really means is that if we just consider a normal metal, we have a band like this. If we double it, if we don't double it, it's difficult to open a superconducting gap. This looks very ugly. So that's why we double the basis and we can open the gap. But this also means that we now have two degenerate, or not degenerate, but two eigenenergies that are related. And we can then write our Hamiltonian in a diagonal form where all these new gamma operators are now independent fermion operators. So now we can calculate all the observables by relating known quantities to these new observables and evaluating the Fermi-Dirac distribution as the expectation value of these operators. And we are typically interested in the superconducting gap, which we calculate self-consistently. But we can also calculate other types of superconducting correlations. And the most interesting one is the odd frequency spin triplet correlation, because this is of an S-wave type, so it's much more robust to disorder than the other types of triplets. And one of the strong points of this methodology is that we can calculate the free energy and determine the ground state of the system, which is more tricky to do with some of the quasi-classical methods. Now, let's get to some results. We first started out by considering the critical temperature of first a ferromagnet superconductor ferromagnet structure. and then switching one of the ferromagnets with an antiferromagnet. And here we see the critical temperature as a function of the tilt angle of this second ferromagnetic layer. And at zeta equal to 0, that is for a parallel alignment, the FSF structure has a minimum critical temperature as expected, because now the spin splitting field inside the superconductor is strong. While if they are antiparallel, the spin splitting field partially cancels out and we have a much higher critical temperature. Now, what you can notice for the structure with the antiferromagnet is that there's no difference between up and down, because we have the two sublattices, one pointing up and one pointing down, which means that there cannot be any such thing as a difference between the parallel and antiparallel alignments. And because of this, we're able to pick out the second mechanism that I talked about, namely the mechanism of whether we have just opposite spin triplet for a parallel alignment or equal spin triplets for a perpendicular alignment. And this is exactly what we see here, that for zeta equals to pi over 2, there's a suppression in the critical temperature owing to this equal spin triplets that can more easily leak out of the superconductor. Now, we can also consider the free energy, and that typically behaves opposite of the critical temperature. Here we study first, we can just set the superconducting pairing to 0. Where did my mouse go? Okay, we just set the critical temperature to 0 here for the red curves, and we set the pairing to 0 in these curves and compare to when we have a superconductivity in our system. And as we reduce the temperature below the critical temperature, we see that the free energy changes. So it now goes from having the minima here at perpendicular alignment to having the minima at the parallel alignments. And this means that if we lower the temperature below the critical temperature, we can in principle have a reorientation of the spins in the antiferromagnet, and we can potentially use this magnetization of the ferromagnet as a control over the direction of the Neal vector. And just to give you some experimental context, our collaborators in Madrid, led by the group of Farkad Aliyev, has shown that if you have a superconductor ferromagnet structure where the spin-orbit coupling is what is breaking the symmetry between these different directions, you can actually have a reorientation of the magnetization as you go below the critical temperature. Now let's zoom in a little bit on this triplet picture. We see here the superconducting gap as a function of the position. And we see that in the superconducting region, if we have parallel alignment, we have a suppression of the gap compared to perpendicular alignment. And if we now look at the odd frequency spin triplets, here particularly in the inset close to the antiferromagnetic interface, we see that the triplets now coming from the generated here at the ferromagnet, they have different behavior when you have a perpendicular and a parallel alignment. That is, when it's parallel, it dies out rather quickly, while here in the red curve, where it's perpendicular, it can leak far inside the antiferromagnet due to this triplets being equal spin compared to the antiferromagnets. Now, I cannot talk about this topic without pointing out this very good paper where they studied antiferromagnet superconductor structure, and here in particular, you just see a normal metal band here, which, if we consider an antiferromagnet, we now don't just have the lattice constant as our periodicity, we have two sublattices, which means that we double the length of our periodicity, which means that we have to make the Brillouin zone half. And in this case, we have to fold the bands inside. And now we don't anymore have just the option of creating a Cooper pair between these 2 points, which is the conventional spin singlet pair. We can also create a finite energy pair between here and here. And this is what they called a Neal triplet, which is a type of odd frequency spin triplet, which can either be seen as finite energy or finite momentum, depending on whether you look in the folded or extended Brillouin zone. And this type of triplets is much stronger when the chemical potential is small, because we want this energy difference to be small. Now we joined forces and we started studying these antiferromagnet superconductor antiferromagnet structures. And if we now look at just the bilayer, we see here that if we consider an insulating antiferromagnet and we just look at how the spin splitting induced on this first layer of the lattice creates spin triplets inside the superconductor, we see that the sublattices are extended inside the superconductor, so we get this beautiful checkerboard pattern. And even though these spin triplets oscillate over the lattice constant, the magnitude of them decay over the coherence lengths. So they can actually affect the properties of these materials similarly as if you consider ferromagnets, just because the length scale is not determined by the oscillations, but the coherence length. Now, if we put the second antiferromagnet, we see that for parallel versus antiparallel alignment, we can either have constructive or destructive addition between these 2 triplets. And since, well, here we consider an odd number of layers in the superconductor. If we have an even number, this switches, so the parallel gives destructive and the antiparallel gives constructive. Now, if we consider the critical temperature in this system, if the spin splitting in the antiferromagnet is sufficiently strong, we can, by rotating these antiferromagnets with respect to each other, we can go from a finite critical temperature to a complete suppression. And if we consider odd and even number of layers, the behavior will be opposite, because we go from destructive interference here to constructive and opposite. If we consider weaker spin splitting field, we get this very beautiful sinusoidal type curves, and this can be fitted to this kind of expression where dominating part is the cosine theta term, and that is shown by this blue lines here, which is the coefficient of the cosine term, and it oscillates as we increase the thickness of the superconducting layer. The second term is the sine squared term, that is if we consider parallel versus perpendicular, and we also get a contribution from that, but it is much weaker and it just decays without oscillations. Now, similarly, we can consider the free energy in this system, and it takes a similar form where the cosine theta now have become a dot product between the 2 Neal vectors, and the sine squared term has become a cross product between the 2 Neal vectors squared. And the coefficients take a similar form where the blue curve here shows the coefficient for the dot product term still oscillating, while the cross product square is decaying and much smaller. And what this actually means is that we now get spin triplet mediated exchange between the 2 Neal vectors, so that as we go below the critical temperature, the superconductor helps mediating an exchange between the 2 Neal vectors. Now, in the end, I just wanted to mention this paper that I found quite interesting because even though there's not been so many experiments on this topic yet, there was this this experiment on a 3 sublattice antiferromagnet where they showed that under an out of plane magnetic field where they tilt all the sublattices a little bit out of plane, you can get this very long range triplet currents for very, like when the distance between the two superconductors in the Josephson junction is very, very long. Yeah, so that's something I'm still interested in, and I think there's a lot of interesting things in this topic that can still be explored. So just to summarize, we've seen that this compensated antiferromagnets actually affect the properties of the superconductors, and we can use them for critical temperature modulation, control of the Neal vector orientation, and this spin triplet mediated exchange between the antiferromagnets. And in the end, I would like to just mention my wonderful collaborators, my PhD supervisor Jakob Linder and Sol Jacobsen from NTNU in Trondheim, Akash and Simran from UAM in Madrid, and Irina Bobkova, Grigory Bobkov, and Valeria Gordieva from MITP. So, thank you very much.